Hello, and welcome to Developer Live Cloud Native Apps from Oracle. This talk is on data science for developers, leveraging the cloud native services. My name is John Peach, and I'm a principal data scientist on the Oracle Cloud Infrastructure, Big Data, and AI team. The agenda for this talk, we'll go over an overview of the OCI data science service and the platform that it sits within. We'll then do a demonstration of how to use the software, how to set up your system, create a project and notebook, and then we'll go in detail through a model that we're going to build out using the accelerated data science library. Then we'll come back and do a quick summary, and we'll follow that up with some questions and answers. The key takeaways that I would like you to have from this talk is that we need to integrate data science with the cloud. No more doing data science on our laptop. The data's gotten too big, the systems are too complex. So the data science platform is built to do that type of thing. We also want to automate as much of the work as we can. So we want to automate feature engineering and building models using auto machine learning. And then once we have that model, we want to understand what the model is doing. So within the ADS library, we've built in all kinds of great tools around model explainability that will allow you to understand the global and the local effects of what's happening within the model. This will not only help you understand what's going on in the model so that you can go back and tune the model, but it'll help you understand what's going on so that you can explain it to other people. So where does the data science service sit within the cloud? On the left-hand side, you'll see that we have a myriad of different data sources. And then we can pull those data sources in through like the data integration service, which is an ETL tool, or streaming services. And we can pull that into our data warehouse, Cloud SQL, data flow service, which is a Spark service. And this all gets wrapped up in the OCI data catalog. So you know where your data is sitting and how to access it. On the right-hand side, we have the data science services and what that integrates with. So we integrate with everything on the left-hand side, with the data cloud, all the data sources, and then the data science service will talk to the Oracle Analytics Cloud, applications, and cognitive services, so that the data science service is sitting in this ecosystem that allows you to get at your data. So the Oracle Data Science Service is built for artificial intelligence and machine learning workflows. We have CPUs, GPUs, massive storage, powerful network, and we want to leverage them in doing our data science. You'll have access to databases, data lakes, access to integration services such as streaming or data integration. And then sitting on top of that is the OCI data science service. We have model catalogs, projects. You'll do your operations in Jupyter Notebooks, which is a familiar environment to data scientists and software developers. We'll have model training, model deployment, be able to manage and explain our models. And very importantly, this is all built on open source tools that you're familiar with. We've also developed the accelerated data science library with auto machine learning. And basically, this is a bunch of tools that will help you get to your data science faster. The bulk of this talk will be a demo, and we'll be doing a modeling exercise. We'll obtain the data, we'll do exploratory data analysis, and we have a whole bunch of tools that automate that for you. It's a very repetitive task. Then we'll go over feature engineering in a way that's automated and auto machine learning. Then we'll talk about the model catalog. This is the Oracle Cloud Console. And the first thing that we'll need to do is build out the environment for doing data science. This is a one-time operation. It's made very easily. What we'll do is we'll go over to the Oracle Resource Manager and we'll click on Stacks. Then we'll click on Create Stack, Simple Solution, select a solution, Data Science, select Solution, and then we can just choose the defaults. And this builds out everything that we need to work with the data science service. So I don't actually create that, I have one already. Once you have the stack created, you would come here and you go Terraform Actions, Apply. And that would build out your stack. I already have a stack built out, so we won't do that. It just takes a couple of minutes. It's a one-time operation. It sets up all your permissions and resources and stuff like that. Now we're going to go over to the data science service. We're going to click on projects. And a project is an environment that allows you to wrap up a whole bunch of notebooks. So notebooks is where you actually do the work. The project is the collection of notebooks. So you can create a project simply by clicking create project and filling this out. I've already created a project. Then within a project, you can have a bunch of notebooks and notebook sessions. So notebook sessions are basically compute resources that you can use and then have notebooks inside of them. So you would just simply click create notebook and you would fill this out and you can choose the type of CPU that you want, GPUs, the amount of drive space you need, and then your networking configurations. So I already have one of those created. So I would click on this and then I would activate it. It's already active, so I would click on open it. So this is my notebook session that I have. On the left-hand side here, we have the launcher. And under the launcher, we have all kinds of great notebook examples that we've built out that show you different techniques, how to integrate with the services. So you would click on this and you would choose the notebook. So the notebook that we're going to go through is binary classification transportation. So we click on that and launch it. I already have it launched over here. And so this notebook is trying to build a classification for attrition. So we have employees that are going to be leaving the company or not leaving the company, and the company wants to predict that. So this is the traditional Jupyter notebook that all data scientists are familiar with. And we're going to load in the data set. So we're going to be using the dataset factory, which is part of the Accelerated Data Scientist service called ADS. And it does a bunch of things other than just loading in the data. We're going to tell it what the target is, what feature we're going to try to be predicting, and we're going to set a positive class. So it's not just loading in the data, it's loading in the data and establishing information around what we're going to be doing. And the ADS library will use this when it's generating other information for you. So what other information do we generate? So we've loaded in this data set and we have this show in notebook. And we can click on summary and it will tell us an analysis of the data that we have. So we have 29 categorical features, 4 ordinal features, 3 constants. We can then look at the features. So it gives us a breakdown of the different features and then the traditional statistics around it. So 2 keys 5, plus whether we have missing data, whether our data is skewed, that type of thing. For each feature, it also uses intelligence to figure out how we should graph it. So here it's showing that we have our attrition feature, we have a true and a false, and it's showing us the proportions that we have between them. It has age data here, and it lists out the age data, which shows that, hey, we have a very narrow age range and it's slightly sloping down. And then there's other things you can look at, like, so here we have commute length, and the system has determined that it's a categorical variable. But by looking at this, we say, hey, actually, this is not a categorical variable. This really should be a numeric value. But the system, because it was a bunch of discrete integers, thought it was categorical. So we could go back and correct this. So it's very easy to spot these mistakes when you're using this tool. It also shows information around correlations, and it does an analysis of the data and says, hey, there are these problems of the data that you should be aware of. So we might want to go and correct those. It has the ability to show us information about our target. So here we're trying to predict attrition, whether somebody leaves or not. And it uses intelligence to figure out how it should be plotting that information. So if it was a continuous variable, we would have a different type of plot. So here, this lets me know that, hey, my attrition information is very highly skewed, and it makes sense that fewer people leave the company than people that actually leave the company. Now that we've done the exploratory analysis, we want to fix the data as best we can because we've discovered all these mistakes. So we've built in this machine learning technique called Autotransform. And what Autotransform does is it looks at your data and figures out how it should correct it so that when you do your modeling, that you have the best type condition data that you can. There's also a method called suggest recommendations, which you can just drop into here, and it will bring up a dialog window where you can go through and select what you want it to do, but it gives you the recommendations. So now that we've done our automatic feature engineering, we can go and start looking at building some Oracle auto machine learning models. So in this case, what we're going to do is we're going to split the data into our standard test and train set. Then we're going to create an auto machine learning model, and we're going to build two classes of models. We're going to build hundreds and hundreds of models, but two classes of models. So we're going to do a logistic regression and a decision tree. So we go ahead and we run that, and then we can use the get score, and we're going to tell it we want accuracy, and it gives us back the model accuracy. We can get information on what types of models it built. So most of the time it was building logistic regression models, and it built a few decision trees, but it found that the decision trees probably weren't very good. So it spent most of its time and effort on the logistic regression models. Then we can see what it was actually doing. So for the predicted model that it chose, it built out a bunch of different models. Each dot here represents a model and how many features it selected versus its predicted mean score. So as we can see, as more features were added, the model did better. We can also look at hyperparameter tuning. So how many iterations were actually done? And what we see here is that the model score was very flat in the beginning, but right around 17 or so iterations, we started to see rapid improvements in the model. We also support models from other sources. So it does duck typing. So if it looks like a model and acts like a model, we can treat it as a model. Before we use the ADS model, but you can use any scikit-learn models that you want. And now we're going to look at the evaluator. So we have our models built, and we want to see how they're performing. So we built actually 3 models. The machine learning model, based off of ABS. When we build that model, we automatically get a baseline model, and that is the model that's called zero inference, or the null model. It's the model that really doesn't use any information. It basically just predicts the mean most of the time. And then the model that we built using scikit-learn. So we can plot these out, and we'll get our standard receiver operator characteristic curves, our precision recalls, and our lift gain curves. And we're getting these automatically because it understood that it was a binary classification model, and this is how we evaluate models. If we had used a different type of model, it would give us a different set of charts. So there's no need for you to figure out what type of chart you should be using or anything like that. You just go ahead and call the ADS evaluator, and it does the logic for you. It also gives us our standard confusion matrix for each of the models and the dummy model. It gives us the proportions as well as the counts. We can look at the metrics for the model. And so on the test data, we can see that the AutoML model did really well. There was in the accuracy and the Hamming loss. The Hamming loss isn't really relevant for this type of model. They were comparable. The random forest did slightly better on precision, but on recall F1 and the ROC AUC, it did better. It also gives us information about what it did on the training model. So you can see here in the training model that the random forest did much better, but there's some red flags here. So the AUC and the precision are extremely high, but when we go back to the test data, we're not seeing that type of thing. So this is a suggestion that the random forest model was overtraining, where the AutoML classifier is sensitive to this and tries to build around it. Now, all errors within the data, classification errors, are not weighted equally. So we have this method called calculate costs, where you can specify weights for the true negative, the false positive, the false negative, and the true positive, and it will calculate the cost for each model based on the data that you gave it. It's a very quick and dirty way of comparing your models when the cost of errors are not equal. And these costs can be different. For example, you're developing a cancer test, and the cost of missing cancer detection is much higher than falsely predicting cancer when there is no cancer. So that's when you would use this. One of the most interesting things about the ADS library is the model explanations. I think this is revolutionary. A lot of what data scientists do is build black box models, and we truly don't understand what is going on inside of them. And that makes them very difficult to explain. It makes them difficult to go back and tune them because you're not quite sure what's happening. And the Oracle Research Labs has put a lot of effort into developing model explainability that we've been put into the ADS library. And there's two types of explainability that we'll be going over. There's global explanations where you're trying to understand the general behavior of the model. And then there's local explanations where you have a single observation and you want to see how that observation is going to behave. And these techniques are agnostic to the models themselves, so that you can throw in any model that you want and it will build explanations around it. So we have this ADS explainer module that will load in here, and we're going to pass in our test and our model. And then we're going to call global explanations and use the MLX global explainer object. So you can write your own providers, but it comes with a global provider and a local provider. So one of the first things that we want to look at is feature importance. And so we have a method that will basically describe to you what feature importance is, how to interpret it, and then some references for you to go read. So for this model that we're looking at, we have the feature importance. And what it's telling us is that if an employee is working overtime, they have a higher probability of leaving, quite significant. If they're married, it's slightly increased. If their job involvement or years since last promotions, these are the factors that play into the model that are most important. Well, we had around 28 features put into the model. There is these ones here, which are the most important ones governing. So these are actionable. So if an employer wanted to take an action, say, okay, we want to retain our employees, what can we do? You can do things like reducing the amount of overtime, and that's going to have the biggest effect. We can also look at the detailed information around the feature importance. So it's possible that for some employees, overtime is really important because they want the extra money, and other employees, they don't necessarily want the overtime. So we can look at individual observations and see how important they are. And what we're seeing here is that we have a nice even spread. We don't have a chunk here and a chunk over here. So it's telling me that this feature is important and it's universally important across all employees. We can get access to the raw data. And here is the random forest model where it's picking out different features. It's definitely saying that overtime is important. It's not as important. The bar looks the same length, but the number is smaller. But other things such as age play into a factor. There is also two other very important plots that you can use. One is called partial dependence plot, and the other one is called individual condition expectations, or ICE plots. And what these tell us is information around how the different features interplay with each other in building the model. So we provide a summary function here that prints out information on what the descriptions are, how it works, how to interpret them, and then gives you some references that you can go read up some more details on. And then we can actually see the PDP plot. So PDP plots allow us to plot one feature versus the outcome, or multiple features versus the outcome. So here we're just plotting whether or not there's the effect of overtime, whether or not an employee leaves. So P true is the probability that an employee will leave. So we see that this is an important, not just an important feature, but it's important in predicting what the outcome will be. But it doesn't tell the full story. So PDPs work on what's called the marginal probability. They basically take everything in this overtime category and just sort of average it together and see what the effect is on the probability calculation. But let's say there was two groups where one group wanted to have the overtime and another one didn't. So we would want to split that out. And that's where an ICE plot is really good. So here we're doing the same thing. We had the ICE plot. So this is the probability of false. So let's look at the probability of true, because that's the same comparison. And what we're seeing is that now we're getting a distribution, and we can move the mouse up and down and see different values. So for those that don't have overtime, the effect is pretty universal, that it has very little effect on whether they'll leave or not. There are some rare cases where people leave, but in general, it has very little effect. And then you go over here and you look at the yes distribution. So what this is telling me is that there are a chunk of employees that do work overtime, that it has very little effect on whether they leave or not. But there is this tail of employees where there's an increasing probability that they will leave. And if you notice, the shapes of these two distributions are very different. So we have two different behaviors going on. So as the data scientist, it will help me to help understand what's happening and go back and reinterpret and modify my model. I might want to get more data so that I can throw it into the model to see if we can piece out the differences between these two groups. One of the great advantages of the PDP plot is that we can plot not just one feature against the predicted outcome, but we can plot multiple features against the outcome. So here I'm doing overtime versus the job level, and then the color indicates the probability that employee will not leave. So for a job level 3, if there's a lot of overtime, there is a fairly low probability that they'll leave. If it's a job level 2 and there's overtime, there's even less probability that they'll leave. So basically it's saying is, as the job level is going up, there's a difference in an effect that we're seeing in the probability that somebody will leave. So we're generating these plots with just a couple of simple commands, and we're giving you the information to interpret and understand them. Now, what happens on the local level? So PDP and ICE are on the global level, where it considers all the data together. On the local level, we want to take a single observation and see how that observation behaved within the model. So we provide information around interpretation, the description, some references. So now we're going to take this one observation here. We have a 28-year-old employee, infrequent travel for work, salary level, they're a software developer, a bunch of other information about them. So we're going to call the local explainer. We're going to use the MLX local explainer object before we were using the MLX global explainer object. And this gives us a ton of information on what the model actually did. So we predicted false, and the model targeted the true value was false. And then here we have some features. But if we go over here, we now have the explainer. So the explainer that we used was called Lime. It's a very popular explainer, and a legend on how to interpret some plots. So the explanation plots here tell us what features we had and how they affect the probability that an employee would leave. So the probability that an employee would leave if it's no, which was the case for this employee, dropped the probability down significantly by 19%. But number of companies they've worked for was very high, and that increased the probability by 0.12%. So we can see this for each feature, how each feature is playing a role. So we could look at an individual employee and identify whether or not this employee is at risk or leaving or not by understanding these features. So like if this employee was close to leaving and we start to give them overtime, we might increase the probability that they're going to leave. We also have, I won't go into details, but plots on understanding the quality around the predictions that we're using. So what did we go over? So we talked about creating the Oracle stack using the resource manager. We talked about how projects are used for collaboration, and that the bulk of the work is done in notebook sessions. And then we talked in detail about the accelerated data science SDK that we have available. This really helps developers get up to speed in data science and data scientists to understand what is going on in their data without writing a whole bunch of code. Up on the screen is some links to some product information. The first link is a link to a course that you can take where you would actually go through the notebook that we talked about. So you can get some hands-on experience and actually see how the ADS library works. We also have links to the general product information, the documentation for the ADS, the REST API, and some Oracle functions, which are used for model deployment. So the key takeaways from this talk that I want you to remember is that your data science platform should be integrated into the cloud. The days of doing data science on the laptop are gone. You need to be able to access extensive resources and integrate that into your data science and build out models. We want to solve our data science problem where it's hard to hire data scientists, and we could use developers by automating a lot of feature engineering and machine learning tasks as well. We also want these people to understand what it is that their models are actually doing so that they can explain them. So we've built out extensive tools around model explainability. We have a few minutes, so let's take some questions from the audience. So the first question is, how does ADS help software developers do data science tasks? That's a great question. So there's a problem within industry in that it's really hard to hire data scientists. Generally requires a graduate degree, and a lot of the low-hanging fruit can be solved by having software developers use tools that help them build models and understand them. So the ADS library is targeted towards not just the expert data scientist, but also the software developer that has an interest in machine learning, but not necessarily the background for it. So the tools that we went over covered things like doing feature engineering, where we had a system that would use its machine learning intelligence to automatically do that feature engineering for you, or you could go in and have it make recommendations, and you could change up what is going on. You could try different types of feature engineering. We also saw that in the exploratory data analysis portion that it's fairly simple to do an exploratory data analysis, but it's very repetitive, and it's something that software developers aren't necessarily used to. But by having this tool that builds out the feature analysis for them, the exploratory analysis for them, sorry, they can take that as a basis for learning how to do this and identifying problems in the data and expanding upon that. We also saw that the AutoML libraries were really good. They were predicting better than if you had just done a random forest, and that it builds all kinds of intelligence into the system so that the software developer doesn't necessarily need to know all the nitty-gritty details of how the algorithm is working. That gets handled for them automatically. So these are very important things for getting the developer up to speed into doing the easier sort of machine learning stuff as they advance their career without going and getting a graduate degree in machine learning. We also have the tools in there for model explainability. So you get to really understand what's happening in the data without having an intimate mathematical knowledge of what's happening in the algorithm. Thank you for the question. The next question is, why use a cloud-based solution such as Oracle Data Science instead of just using Jupyter Lab on my laptop? Yeah, so historically, this is the way that people have worked. You build out a model on your laptop, and then you sort of throw it over the wall and have engineering productionalize it. But that doesn't really work with the systems that we have and the volume of data that we have. It's generally not possible to crunch a lot of the data on a laptop. When your laptop is being fully utilized to build a model that's going to take 24 hours, what else are you going to do? So having this stuff in the cloud where you can spin up little machines while you're doing your initial work, and then when you do the big compute, you can spin up very large machines or use distributed clusters, helps a lot. It also really helps to have the data being in the cloud, in your autonomous database, and having an environment that's automatically connected to those so that you're using that information without having to pull it down on your laptop. There's regulatory and security issues around that. There's volume sizes around issues around that, but it's just there and you can just access it. We also provide access to things like the Vault, which is a system for storing encrypted data so that you can have your passwords for your database not stored in your notebook, but stored in the Vault so that you can control who has access to the data while still sharing that notebook. Gone are the days where one data scientist works in a notebook and nobody else ever looks at it. Data science has become much more collaborative, and having a cloud-based platform that has collaboration built into it really helps the data scientists share their work, have conversations with other people, work in teams on particular projects. Also having things integrated, we didn't talk about it, but the ability to, once you produce the model, this has typically been a bottleneck for data scientists. They build the model and then they have to hand that model over to an engineering team that then has to prioritize it and release the model. With the integrated system that we have, it's very simple for a data scientist to take that model and deploy it in a way that that model can run in production without the use of a large engineering team to support it. So it sort of prevents that bottleneck. The data scientist or the developer can own the data ingestion portion to the model building portion to productionalizing that model and then reevaluating that model and sort of producing that model life cycle where they sort of repeat that process over and over again. Thank you for the question. Next question. Once I have a model, how do I deploy it into production? So following up on what we were talking about, there is a service called the Model Catalog within Oracle Data Science Service that allows you to take that model and create a model artifact. And that model can either be an ADS model, which is a model that's built off of the ADS library, or it can be a model that is like from scikit-learn or something like that. It can be any generic model. And we put a wrapper around it and we push that to the model catalog. And now that model becomes immutable. You can't change that model. If you want to change it, you have to pull the model back into your notebook, a very simple one-line command to do that, make changes and then push it back out. So this model immutability allows us to track what models are in production at what time. So it's very common for a data scientist to release a series of different models that they're going to run on different groups of people, different tests, A/B testing, like the blue button model and the red button model, and see how they perform. And you want to keep track of that. You might release a second version of the red button model. Now, did you overwrite the first version? Well, with the model catalog, you can't do that. It's still there. So you have this provenance, as they call it, between the model that you produce, the data that you're collecting in production, and the ability to go back and iterate on that model. So that's a very important tool that we've built out. Currently, we're using Oracle Functions for this. We're going to be releasing in 2021 a new version, which is optimized for machine learning models, because machine learning models behave a little differently than sort of what Functions was designed for. So we're very excited about that upcoming feature. And it will basically be a similar integration. It'll actually be a lot easier to use because it's going to be tighter integrated into our service than Functions are. And it will allow the developer and the data scientist to own end-to-end model production, evaluation, and everything. So thank you very much for your questions.